Good day. I am David Frizzell, and I am presenting a slideshow called The Vastness of the Universe. We at the Albuquerque Astronomical Society are participating in this year's virtual Cosmic Carnival through the auspices of the Albuquerque Open Space Visitor Center. The Albuquerque Astronomical Society, or TAAS, is one of the largest amateur astronomy clubs in the country, with over 300 active members. We have a private observatory, a number of telescopes that we lend to our members, an active educational and public outreach program, and a number of ways that we share the science and fun of astronomy. Our motto is observe, educate, and have fun. You can find out about our activities at our website and Facebook page. I will give some more details at the end of this discussion. Our discussion of the vastness of the universe is going to look at the various dimensions of time, distance, speed, and mass, and all in light of what is generally known in astronomy and astrophysics. We will look back a bit on how some of our knowledge was acquired, and we will bring the picture forward to 2020. On a beautiful, clear night, the stars seem so close you could almost reach out and touch them. How far away are the stars? What lies beyond the stars that we are able to see with the naked eye? Just how large is the universe? This picture was taken by the Hubble telescope. It shows countless dots that are, when you examine them, individual galaxies and not stars. The universe is so vast that it is easier to describe it using 4 different sets of measurements. Our 4 measurements, which we've divided into chapters, are huge distances, huge objects, huge numbers of objects, and huge periods of time. Distances in astronomical terms are so great that we actually use the speed of light and the passage of time to describe the distances. On Earth, we are used to thinking of distances in inches, feet, and miles, or their metric equivalents. However, distances in space are just so great that those measurements would not be very useful. Just imagine if instead of describing the distance from Albuquerque to Denver in miles, I said 26,991,360 inches instead of 426 miles. Astronomers use different measurement units, but particularly the light year. A light year is the distance that light travels in empty space at a speed of about 300 kilometers per second, or about 186,000 miles per second. That means a light year works out to about 6 trillion miles. If we apply the speed of light to distances on Earth, it takes 1/100th of a second for light to travel across the United States. And light would travel around the Earth about 7.5 times in 1 second. When we start applying the speed of light to astronomical objects, it makes a little more sense. Instead of saying the moon is 238,000 miles away, we can say it's only 1.25 seconds away. And instead of saying the sun is 93 million miles away, we can say that the sun is 8.3 minutes away. After the sun, the nearest star is Alpha Centauri, which is about 4.3 light years away. That is easier to say than 24 trillion, 854 billion, 850 million miles away. And the brightest star in our night sky, Sirius, is about double that distance at 8.7 light years. So as you can see, the distances between objects in space are so huge that it makes sense to measure them on a scale of light years. But that scale is a bit too large for measuring most individual objects such as planets and stars. For that reason, we generally use a comparative scale for individual astronomical objects. For comparison scale, consider using the sun as our primary object, and let's set it at about 1 foot across. If we shrink the size of the planets and their distances from the sun on the same scale, we get these numbers, which shows that even the biggest of the planets is barely over an inch in comparison, but quite a few feet away. And yes, I know that Pluto doesn't officially count as a planet these days, but you can see how tiny it is when compared to the sun. The comparison scales and the models that come from them aren't quite as useful when we get outside our solar system. I'll come back to that a little bit when we talk about the size of stars. With the sun at 12 inches across, we are 35.5 million miles from the center of the galaxy that we are in, the Milky Way. And those numbers are a lot more cumbersome than the approximate 28,000 light years measurement. Once we leave the Milky Way galaxy, the distances grow increasingly huge. The closest galaxy to ours is Andromeda at about 2.5 million light years away. Another close galaxy, the Southern Pinwheel Galaxy, is 14.7 million light years away. At greater distances than about 1,000 light years, you can see that it becomes easier to use larger scales, such as the parsec, the kiloparsec, and the megaparsec. We even have something called a gigaparsec. At gigaparsec scale, we measure the observable universe, said to be about 28.5 gigaparsecs across, or about 93 billion light years. I will return to this dimension at the end of this talk. It's really outside the scope of this discussion, but there are a number of ways that astronomers measure these huge distances. These are just 4 of the most important relationships for measuring distant astronomical objects. So that ends our first chapter, or our first dimension, which is the distances between objects in empty space, as opposed to the size of objects. But we are now going to see that those objects themselves are very large. In this section, we're going to talk about the size of objects, and we'll do both some comparisons by scale, as well as some measurements. Earlier, we compared the sun, Earth, moon, and planets on a scale where we set the sun at 1 foot in diameter. Let's look at those relationships modeled on the same scale. This shows how impressive our largest planet, Jupiter, is when compared to the Earth. Now let's use that same approach and compare Jupiter to the size of the sun. So you must be thinking at this point, well, the sun's a pretty big object, isn't it? Take a moment and look at how much larger some of these other stars than our sun. Look at how much larger Arcturus is compared to our sun. And now look how much larger Antares is compared to Arcturus. And Antares is not the biggest star. The largest star we've identified so far has the wonderful name of R1356A1. You can only see it using special interferometry in the southern hemisphere. But if you're really curious, it's in the star cluster in the Tarantula Nebula. Okay, stars are large, but as objects in the universe, they are not very large, since nearly all stars are found within groups. We refer to groups of stars as galaxies, and we measure galaxies. Earlier, in the context of measuring distances, we considered where we were placed in our own galaxy. If we consider it in the context of size when compared to stars, we realize that a galaxy is, of course, much larger. In fact, our galaxy contains about 400 billion stars. Now that, you might say, is a really large object, but guess what? You guessed it, our Milky Way is not even close to being the largest galaxy. The largest known galaxy has the name IC1101. It's thought to be about 100 trillion stars. It's also about 320 megaparsecs from Earth. In coordinate systems, it's located within the Virgo constellation. You may have guessed by now that since astronomers consider galaxies as objects because they are clusters of stars, that in fact, astronomers think of clusters of galaxies as individual astronomical objects, and they are even larger, of course. Our Milky Way is part of a group called the Laniakea supercluster, a cluster that measures about 500 million light years across and contains about 100,000 galaxies. Superclusters are part of even larger structures that are sometimes called galaxy filaments or walls. Some of you know that right here in New Mexico, we have part of the instruments that perform the Sloan Digital Sky Survey. Using special mathematical tools, the Sloan survey produced this digital image of great supercluster walls, thought to be about 1.37 billion light years long, making it about the sixth largest known object. And of course, we've already talked about the diameter of the observable universe in our first chapter. We think it's about 93 billion light years across. So that ends our second chapter on the size of objects in the universe. Now we'll turn to the number of objects. Chapter 3 on the number of objects is going to be fairly brief because we are really more concerned with things that are larger than atoms and molecules. And as you probably noticed in the last chapter, we are generally concerned with objects larger than planets. Just in our Milky Way, we estimate there are about 400 billion stars. The most current data that we operate with is that we have about 500 billion galaxies in the universe. This image taken by the Hubble Space Telescope is just a slice of the sky. It's only about 1/10 of the diameter of the moon, which is obviously a tiny portion of the sky. But this image is of galaxies, not stars. Just doing some multiplication, we end up with a very large number of stars in the universe. I'm not even going to try to give you a statement of what that number is, so just go with 10 to the 25th. It has been said that this number is approximately equal to the number of the grains of sand on Earth. So that ends our very brief chapter on the number of astronomical objects in the universe. This brings us to our fourth and final chapter on the amount of time that we encounter when we look at the evolution of stars and their lifetimes. Stars and the galaxies in which stars are formed have recognized natural histories involving the accumulation of gases and the fusion of those gases into nuclear cores. This image of the Orion Nebula shows where stars are forming. Gases, mostly hydrogen, accumulate in nebulae and start to collapse into greater mass under its own gravity and start to spin. As the gas accumulates, the core gets denser and the mass spins faster. The gas at the core continues to heat up. The region of heated gas starts to glow and shows characteristic patterns. This image shows using color how a protostar forms, protostar being the early stages of a star. That red line is an outflow of heated gas being expelled from the center as the protostar spins. When the temperature of the hydrogen gas in the middle of a mass of a forming star reaches about 15 million degrees Celsius, fusion begins. The initial product is heat and helium gas. Altogether, depending on the amount of gas that is accumulated, it may take millions or billions of years before fusion actually begins. Once fusion has begun, the collapse of the gas into the core is stopped because of the outward pressure of the fusion heat and radiation. The heat and radiation make the star shine. The star is said to have entered its main sequence phase. As this diagram shows, the next period of time and characteristics of the star's cycle depends on how much mass the star has when fusion begins. A low-mass star, such as our Sun, will coast along for roughly 10 billion years, very slowly expanding and getting redder as helium is fused into carbon. Once the helium has been fused into carbon, the outer layers of the star sort of drift away, creating a gas envelope and leaving behind a hot core called a white dwarf. For mostly historical reasons, that gas envelope is called a planetary nebula. This sequence shows that our Sun is about halfway along its journey to becoming a red giant. In other words, it's just a little over 4.5 billion years old. Stars that begin more massive than our Sun, at least 3 times more massive, will move much more quickly to the stage where the hydrogen has been fused and begin to fuse its helium. A massive star's helium fuses quickly. In a period of about 1 million years, different shells of different elements will start to form around that core, and eventually it ends in an iron core. And as the iron core develops, it suddenly collapses and explodes in what we call a supernova. These 3 images will show you a little bit about how a nova might appear if we saw it in a telescope and we were lucky to catch it. This is an image of a 2016 supernova that was near the constellation Draco. And the image you see in the middle, which is another fraction or a part of a galaxy, is not Draco itself, but it's useful for you to see where the nova appeared relative to the spiral arms of this small irregular galaxy. It's about 3.6 billion light years away. This particular star that blew up in 2016, or at least that we saw in 2016, was estimated to have a mass of between 50 and 100 times that of our Sun. As you might expect, since stars have life cycles, then so do the galaxies that are made up of stars. And in terms of just their shape and how they manage to maintain their coherence, we're talking billions of years. The galaxy that you see here, we believe was formed about 13.4 billion years ago. Or to put it another way, just about 400 million years after the Big Bang. So, to summarize, galaxies live for billions of years, although they may change their shape over time. And, of course, referring once again to our own universe, it is not just large, as we've discussed, or massive, as we've discussed, but it's also the oldest thing that we know at approximately 13.77 billion years. That concludes this very brief survey of the vast measurements, scales, and quantities that we use and understand about our universe. You can see what we mean when we say these things are astronomical. I've been pleased to present this program on behalf of the Albuquerque Astronomical Society. I hope you will look us up on our website, www.taas.org, and consider learning more about astronomy. Good day.